ちは。私は Samuel です。
Hello, I'm Isabel.
We are talking about wireless power transfer. Let's have an overview of what the video is about. First of all, we are going to talk about what is WPT, why, types, advantages and disadvantages, application as well as future modifications. What is WPT? Wireless power transfer is the transmission of energy wirelessly. You may ask me, why not wires? As per studies, most of the electrical energy transfer is through wire. Well, most of the energy loss is during transmission using wires as well. On an average, it is more than 30%. In Australia, it even exceeds 40%. Why WPT? First of all, reliable. With less energy loss, high efficiency. Without the need of wires, low maintenance. Now, we will look at the types of WPT. Basically, WPT consists of inductive coupling as well as resonant inductive coupling. This is how inductive coupling works. Electric current is first applied to a coil of copper wire producing a short range of magnetic field. A second coil is then placed within the magnetic field and electric current will flow through it. The electric power has transferred from one coil to another through magnetic field and what we know as induction. Induction is what charges a wireless electric toothbrush. It works well over extremely short, very short distance. Once you pull the coil apart, power transfer ceases. To make the power transfer longer, we need resonant inductive coupling, and this is what we will see next. Resonant inductive coupling uses the same principle as an opera singer uses to shatter a wine glass from across the room. It's called resonance. For the opera singer, when the frequency of the sound wave matches the unique resonant frequency of a glass, the acoustic energy is converted to kinetic energy. It builds up inside the glass until it shatters. The coil that Y-Tricity uses to transfer power wirelessly are magnetic resonators. First, a rapidly oscillating electric current is applied to a coil at its specific resonant frequency. This creates magnetic field in the region around the coil. Tune a second coil to the same resonant frequency as the source and it will couple, resonating anywhere within that region, and converting the oscillating magnetic field into an electric current within the second coil. This response is called highly coupled magnetic resonance. By attaching the second coil to a device such as the battery of an electric car or a mobile phone, this current can be made to do useful stuff. The source can be either centimeters or meters away from the device being powered and can deliver power through walls or around metal obstacles. The power can even be distributed across multiple devices at once. By a simple trick of physics, power is transferred wirelessly through both methods of WPT. Let's look at the comparison between WPT using the inductive and resonant technology. Inductive coupling gives high power transfer efficiency while maintaining a low frequency of oscillating magnetic field. The vice versa goes for resonant. Inductive coupling uses simple technology, but resonant uses complex technology. We can use multiple devices at a time for resonant, but only one for inductive coupling. Inductive coupling requires careful alignment of device involved, but not resonant. That's all for the comparison between inductive versus resonant. Thank you.
Hello everybody. Let us look at how does wireless power work. The basic of wireless power involves the transmission of energy from a transmitter to a receiver via an oscillating magnetic field. To achieve this, direct current supplied by a power source is converted into high-frequency alternating current by specially designed electronics built into the transmitter. The alternating current energizes a copper wire coil in the transmitter, which generates a magnetic field, Once a second or a receiver coil is placed within proximity of the magnetic field, the field can induce an alternating current in the receiving coil. Electronics in the receiving device then converts the alternating current back into the direct current, which becomes usable power. The diagram below simplifies this process into 4 key steps. Step 1. Power source A is converted into high-frequency alternating current by transmitter electronics. Step 2. High-frequency alternating current flows in transmitter coil B and generates an oscillating magnetic field. Step 3. Energy from the magnetic field induces alternating current in the receiver coil C. Step 4. Alternating current is then converted back into direct current by the receiver electronics, providing power to the respective application. Fritz wireless power transmitter presses an AC signal to the transmit coil. Current flowing through the coil induces a magnetic field that is emitted in all directions. When a second coil is brought in range of the first, the oscillating magnetic field induces current in the received coil. Power can be transferred through solid objects, such as walls, household furniture, and human tissues. Introducing a third coil extends the range of the wireless power transfer. Additional circuitry converts the AC signal into a DC voltage compatible with any application, including implanted LFS. Repeat to be a conclusion, the main voltage is converted into an alternating current signal, which is then sent to the transmitter coil via the electronic transmitter circuit. The alternating current flowing through the transmitter coil induces a magnetic field which can extend to the receiver coil, which lies in relative proximity. The magnetic field then generates a current which flows through the coil of the receiving device. The process whereby energy is transmitted between the transmitter and receiving coil is also referred to as magnetic or resonant coupling and is achieved by both coils resonating at the same frequency. Current flowing within the receiver coil is converted into direct current by the receiver circuit, which can then be used to power the device.
So I'm going to talk about a machine that uses the idea of YPT, wireless power transfer. Okay, so that's quite a lot of machine that uses the idea of YPT, but I'm just going to say a few which is more common and it's easier to understand. Yeah, so the first one I'm going to say it's PowerMet inductive charging spots, which can be seen in coffee shops and restaurants, all this stuff. Yeah, it's quite convenient because customers don't have to bring their charger and don't have to find a plug. They just need to put their device, their laptop or their handphones on that mat, then it can recharge already. So convenient. So the second one is prototype inductive electric car charging system. You guys heard of that before? No, okay. So it's at 2011 Tokyo Auto Show, there's this thing, but I believe there's more of this nowadays because technology is so advanced. So yeah, it's a charger for cars, so you don't have to use petrol. Save the earth, yay. Okay, then the third one is powering drone. You guys heard of that before, right? Okay, it's very common. It's expensive, but lots of people still buy it for movie. So it uses light wave to produce it, and the range is very long, very long. and also powering space elevator climbers. It's an elevator that can let you go up to space. It's a very advanced thing, so maybe probably like in the future there would be this very cool stuff. And also wireless power access card, like credit card, debit card. Nowadays, right, there's like a wave thing. Yeah, so it's like you don't have to like stop your card, you don't have to type your password, you just need to like did, then you can buy that thing already. It's so convenient. Yeah, technology advance, right? Whew. Also, solar power satellite also uses the idea of YPT. So what is this? This solar power satellite, right, collect the solar energy in space and beam it down to Earth. So sort of like we can use energy from the space. Yeah. Then the range is also very long, and it uses the microwave technology to like produce this thing. And also, yeah, finish.
Today, I am talking about wireless power transfer modification. Why do we need wireless power transfer? As Christine said, it's reliable, high efficiency, and low maintenance. That's why we need to modify wireless power transfer to make use of its advantage. Resonant transfer works by making a coil ring with an oscillating current. This generates an oscillating magnetic field. Because the coil is highly resonant, any energy placed in the coil dies away relatively slowly over many cycles. But if a second coil is brought near to it, the coil can pick up most of the energy before it is lost, even if it is some distance away. In order for a wireless power transfer to work efficiently, the frequency of both transmitter and receiver is required to be tuned to the same frequency. For different inductance value of coupling coil, other associated parts of the circuit are necessary to be changed as well in order to get the same resonant frequency. The wireless power is transferred from transmitter to receiver coil using more than a century-old principle called inductive coupling. However, recent developments prove that when two resonant circuits resonating at the same frequency, designed with minimal loss and absorptions, are brought into close proximity, that due to evanescence wave coupling, the energy transfer from transmitter to receiver are at a high efficiency. We can enhance wireless power transfer by using metamaterials and magnetic resonance couples. The reason why we enhance wireless power transfer by using metamaterials is we can increase the range of the wireless power transfer. For the magnetic resonance couples, the effectiveness of the resonance couple system adopting maximum power transfer principle in extending the operating range of wireless power transfer with better power transmission. Metamaterials are a new class of artificial materials that are composed of engineered structures. In the last decade, unique phenomena such as negative refraction and evanescence wave amplification have been predicted and realized in metamaterials. Since the first experimental demonstration of negative index of refraction, metamaterials have been shown to be powerful and flexible in achieving desirable electromagnetic properties from radio frequency to optical frequency. Numerous applications based on metamaterials have been developed, such as superlens imaging devices, invisible clocking devices, and novel antennas. Here we report recent work on the application of metamaterials in wireless power transfer. Next, the wireless power transfer has to achieve a high efficiency. Double the efficiency by using the MRFE, which is Magnetic Resonance Field Enhancer. A MRFE can be something as simple as a copper loop, but it is capable of boosting efficiency by at least 100% as opposed to transferring the power through the air. In order to transfer wireless power, a transmitter coil must generate a magnetic field from which a receiver coil draws energy. The MRFE amplifies the magnetic field while removing very little power from the system. The researcher conducted an experiment that transmitted power through air alone. through a metamaterials and through a MRFE made of the same quality materials as the metamaterials. The MRFE significantly outperformed both of the others. In addition, the MRFE is less than 1/10 the volume of metamaterials enhancer. Energy can be also transferred wirelessly using such diverse physical mechanisms to decrease energy loss like laser, piezoelectric principle, inductive coupling, strong electromagnetic resonance. That's all about the wireless power transfer modifications.